Hey everybody, it's Mrs. Dinkelman. Excuse me, and this is the notes for 8.3. The next two lessons are about these solids that we can create from graphs that we do and how to find the volumes of them. So today's is called the volumes of solids with known cross section. So what we really do with these, if you can kind of picture it in your mind, is we graph some sort of shape, and then what we want is for out of that shape to pop something else, like some geometric shape that we know. So for instance, it's not a great way to explain it. I had a student make this for me. So originally the equation was, it's just a parabola, if you can kind of see that under here. And then what they did is out of the parabola, they had squares pop out. Now what we're going to be dealing with is, what if there's an infinite amount of squares that pop out of that? What does that solid look like? And that's the volume we're really trying to find. Clearly the student couldn't quite do that, but that's what we're trying to do. I know they're kind of on their side. What about if there's a circle that we graph? Okay, so imagine this, and then out of the circle we want there to pop out squares. So certainly the square at the end is going to be a lot shorter than the one in the middle. So the middle, again, it has a width, and then it has to have the same height if that's a square. Okay, so that's that one. I just have a few. So this one is a circle. What if equilateral triangles pop out at us? Okay, so that's what that shape might look like. Again, that equilateral triangle in the middle is bigger because the width of the circle is bigger there, that diameter, versus like the chord that's small on the ends where they're a little bit smaller. Okay. All right. There are some applets, and you probably can Google some online. I'll have one that we look at in class, but I have to do it on my other computer because it's old, and I have to use like Mozilla or something to find it. Anyhow, just a quick reminder about areas of shapes, because what we're going to be really looking for is the area of a triangle or a square or a rectangle, etc. Now, the one that you might not have memorized out of all of these, and again, the AP exam will not give us these, we have to have them memorized, and that's the area of an equilateral triangle. Now, if you're anything like me, I do not recall ever knowing that area prior to calculus, but it's just the √3/4 times side squared. What helps with that is then I don't have to drop that height and try to figure out what it is, because of the equilateral triangle, I am going to know what the sides are. Okay, the way we're going to calculate these is and this is actually going to be the same for 8.4 as well, but what I want you to see in this volume is that we're going to take the integral of the area function. And the way I kind of think of this is, if I have something, an area, and then I multiply it by a dx, which is kind of like the thickness. So let me show you what that looks like. So I have that same triangle piece. Let me just kind of put it back together. Okay, so I have that circle equilateral triangle one, but this one the person built to come apart. So if I can find the area of that triangle and multiply by how thick that is, then I'll have a volume, because it'll be three-dimensional. Now what happens when there's an infinite amount of them is that this dx actually becomes 0, which is why we have to do an integral, because if you remember or don't, an integral is technically a limit of an infinite amount of like rectangles or something else. So in this case, with that kind of picture, it's a little bitty triangles. So I just want you to focus on trying to find the area of the shape that we're talking about. So in example 1 here, they have a picture for us, and they're going to have to tell us whether we're going sideways or not. So this particular one says we're going perpendicular to the x-axis. So just like when we did area, I like to draw kind of a little strip there, so I know we're going this direction. That to me is the bottom of the square. Okay, it says we're doing squares here. And then what I like to do is think of this as a really strange loaf of bread. So I have a square one. Let's see if I can get this one set up as well. So I know this example we're looking at is not a circle, but what I want us to think about, again, popping out of that is the squares. I want us to take a slice out and lay it flat. What I want us to focus on is to find the area of any random square I were to pick out of that solid. Okay, so again, that spot where I drew that green, kind of that's the bottom of the square. I'm going to take that square out. Strange loaf of bread. Here's the slice. I'm just going to like bold that because I want you to understand that that to me is the bottom. Okay. My goal is to find the area of that square. So the way I'm going to find this length of the square, that bottom, is, well, I kind of like to think about area, how I thought about top minus bottom. Well, the top of the square is on this line, and the bottom is just on the 0. So that is just going to be, and I'm going to go ahead and label it, that's going to be that negative 2x plus 2. It is a dx. We're not going sideways. Okay, it's the same as when we were doing area. And so since this is a square, I didn't draw it very well, I also know the sides. The other side is that as well. So the area of the square is going to be that negative 2x plus 2 squared. Once I have my area formula, I actually know my integral. So that area formula is what's going to go in here. And then since this is dx, I need to know where I start and end my x's. Okay. I'm going to stop there on our examples today because you may or may not get to use a calculator. This one we'd actually have to FOIL, and then we could find it by hand. Number 2 actually says set up but do not integrate. So we're looking at the same function, but we're doing different shapes. Okay, so still, does it still say perpendicular? Oh, this one does say perpendicular to x. So let's just do A first here. Perpendicular to x, I just like to draw a little strip in there, kind of like the rectangles from before. This is a dx, and we're doing semicircles. So again, I like to take a slice out of that strange loaf of bread and lay it flat. We're doing semicircles, so the bottom is what's sitting in there. So that negative 2x plus 2, like we had last time, is just sitting at the bottom or on the diameter of the semicircle. So quick reminder that for the area of the semicircle, I'm going to have to do pi r squared divided by 2. Well, the other issue here is that negative 2x plus 2, so it goes all the way along. That's really the diameter. So I think the radius is going to be negative x plus 1. Okay. So now for number 2, my integral is from, again, 0 to 1. Again, we're looking at the x's here, 0 to 1. And it's that pi over 2, which actually is a constant, so you could pull that out in front if you wanted. If we were having to do this by hand, that's probably what I would do, and just multiply by pi over 2 at the end. And then, again, negative x plus 1 squared dx. A lot of people miss that one because they forget there's really like 2 divide by 2's in there. One because it's a semicircle, and one because you have to find the radius, not the diameter. Okay, this time on letter B, we're going perpendicular to the y. We're going sideways. So this is when we have to do all the things in dy, okay? So luckily we know that the y goes from 0 to 2. That's good to know. Rectangle. So I'm still going to draw my picture here. So that's really the bottom of the rectangle. Kind of picked one that was in a weird spot, but that's okay. And so we'll find that in a second. So I like to turn my head on my side. And again, I like to think top minus bottom. Luckily the bottom is 0, but the top is this equation. But unfortunately, I'm going sideways. So I really need to change that equation to an x equals instead of a y. So let's see, y minus 2, and then divide by negative 2. So I'm going to call it negative 1/2 y plus 1. And again, if we think top minus bottom, again, if I have my head on my side, or you can still think right minus left, then it's that equation minus 0. Okay, so that's what's going along the bottom. It says the rectangle just has a height of 1/4. Okay, so that's nice. So our area is just going to be 1/4 times that negative 1/2 y, that is negative. And so our integral is going to have that area formula in it. We could again factor out that 1/4 or multiply it through, keep dragging that together so it looks like it's not. This is a dy, and then we need to know what the y coordinates go from. So again, 0 to 2, lowest y coordinate, highest y coordinate. All right, So this time we have a little bit of work to do because we need to graph it. So let's just go ahead and do the graph first so we can kind of figure out what shape we're talking about, and then we'll kind of read some more. So negative x squared plus 2. So upside down parabola moved up 2. I'm just going to sketch. And then y equals x. So we're looking in that kind of almost banana-shaped area. We are doing perpendicular to the x, so this direction. And they are squares. Okay, I'm going to need to know where we start and end this. So let's just set the two equations equal to each other really quick and find those intersection points. So let's see here, x plus 2, x minus 1. So I'm thinking we're going to go negative 2 to positive 1. And I didn't draw really great, but that doesn't totally make me think that that's wrong. Okay, take a slice out, lay it flat. Again, strange loaf of bread. I think of that as the bottom. And again, when we're trying to find that measurement along the bottom, we're going to think about top minus bottom, just like we did in area. So the top is that parabola, and the bottom is the x. So top minus bottom. Again, this is a square, so the side lengths are the same. So negative x squared plus 2 minus x quantity squared. For the area, I should probably write that. I think the area of this is, okay. And again, we found these earlier because we needed to know where to start and where to end, finding that volume. Circles can be a little bit challenging, especially finding that, like the top and the bottom. That'll be kind of an interesting thing to think about. So they have a graph for us. Let's just do letter A. We're going perpendicular to the y, so we're going this direction. It's kind of unfortunate that we're going perpendicular to the y. I kind of wish we did x, but that's okay. We'll make it work. So these are going to be dy's. Equilateral triangles on A. So again, maybe I can try to draw a little bit better triangle. Okay, that's the bottom of the triangle. So as we're trying to find that measurement along the bottom, I have to think about, again, turn your head on your side because we're doing this sideways. I like to think of top minus bottom or do right minus left. So the problem with this is the top and the bottom are both on the same circle. I guess maybe earlier I could have solved for x equals here. So let's talk about that really quick. X squared would be 1 minus y squared. X would be positive or negative root 1 minus y squared. So normally it's like the top half and the bottom half, but again, we're thinking sideways. So as long as you turn your head on your side, you can still think that. But if you want to think of right minus left, the right-hand side of this circle is the positive square root, and the negative is that left-hand side of the circle. So if I'm thinking top minus bottom, I have to have the positive square root of 1 minus y squared minus negative square root of 1 minus y squared. So really that's just 2, because we add here, 2 square root of 1 minus y squared. When I see it like that, it kind of makes me think, yeah, I just have this same like semicircle doubled. So that kind of makes sense to me. This is that area formula that I told you in my brain I felt like I had never seen before. So we take that side and we go root 3 over 4 times that thing squared. Okay, we need the y coordinates. Not that it matters in this particular situation because the x and y are really the same. Lowest y coordinate is -1/2 and tallest, or not -1/2, -1 and then 1. So for letter A, I think my integral should be -1 to 1. And then I'm going to insert that root 3 over 4. I'm going to run into that mess over there. I better erase it. So there's clearly some simplifying I can do in here, like squaring the 2 would cancel with that 4, and then squaring the root obviously cancels that out too. But I'll leave it there. Again, on a multiple choice, hopefully you could find your right answer. Okay, for part B, we're going to think in a similar way, but this time on part B, we have to think rectangles. So let's think of part B down here. So that base and height, okay. Let's just put that 2 square root of 1 minus y squared down here since it's the same. We're doing perpendicular to the y again. The heights are 3 times their base. Okay, so the height then, I don't have it drawn very well, but that's okay, is 3 times that. And so our area, I guess this time I'll actually simplify. Root times root's going to get rid of that. So same limits on the integral, but a little bit different area formula. So I'm just kind of peeking. It looks like I'm saying number 16 is the problem that I think you should cross out when you come to class, or if you come to class. I will, I'll have that applet for you, and if you have to stay home, I'll try to see if I can present it on my big screen someday. Okay, get to work.